chemistry.
By 1808, Franklin had flown his kite and established that lightning was a form of electricity, and Volta had discovered batteries. But there was no electricity grid, running water, or central heating. Despite these hurdles, in 1808, John Dalton proposed a revolutionary theory that is the foundation of modern chemistry: atomic theory. Dalton hypothesized that all matter was comprised of undividable atoms, and that atoms of a given element were identical but different from atoms of another element. As with most major discoveries in science, as soon as Dalton's ideas were published, other researchers immediately started to ask questions and seek answers to verify or refute Dalton's proposal. Are atoms really indivisible? What is the structure of an atom? What are the differences between atoms of different elements? In this video, we will talk about some of the earliest experiments to understand the structure of the atom and how our understanding has evolved over time. Dalton and other scientists proposed that the atom was indivisible, that it could not be broken into smaller pieces. However, in 1897, physicist J.J. Thomson disproved this theory by performing a famous experiment involving a cathode ray tube. Do you remember old analog TVs where you could see red, green, and blue pixels forming the images on the screen? Well, cathode ray tubes are the basis for this technology. Cathode ray tubes contain two metal plates that act as electrodes which facilitate the conduction of electricity in a circuit, meaning that electrons move from one plate to the other. A high voltage charge moves between the two plates, causing one of the plates, the cathode, to emit a cathode ray, which flows through a tiny hole in the other plate known as the anode. When the ray moves through the hole in the anode and hits a screen at the end of the tube, which is covered in a phosphor, light is emitted, allowing you to watch your movie. Thomson was interested in understanding what cathode rays were. To do this, he placed positively and negatively charged plates on opposite sides of the tube at 90 degrees to the anode. He observed that the small flashes of light emitted when the ray hits the end of the tube were now all concentrated on the side of the tube that contained the positively charged plate. This indicated that the cathode ray must be emitting negatively charged particles that are attracted to the positive plate. Now, charged particles are either attracted to or repelled by a magnetic field. So, in a second experiment, Thomson used a magnet at 90 degrees to the anode to control the path of the cathode rays. Just like with negatively or positively charged plates, Thomson could use the poles of a magnet to redirect the path of the cathode rays. This was important because Thomson was able to measure the deflection of the cathode ray caused by the magnet to determine the mass-to-charge ratio of the cathode ray. His conclusion was that cathode rays were negatively charged, and that their charge-to-mass ratio was very large, meaning that despite the ray's small mass, they contain a lot of charge. Thomson's experiment led to two major conclusions. First, because the mass of the particles was much smaller than that of a hydrogen atom, the particles must exist as part of the atom. Second, all elements must have these negatively charged particles, since the cathode rays had the same mass-to-charge ratio regardless of which metal was used as the cathode. On the basis of these experiments, Thomson concluded that cathode rays are made up of electrons, small, negatively charged subatomic particles that exist in all atoms. The electron is considered a subatomic particle because it is smaller than an atom. Further, because other researchers had determined that atoms are neutral, Thomson proposed the plum pudding or blueberry muffin structure for the atom. Like blueberries suspended in a muffin, he suggested that negatively charged subatomic particles were embedded within a sea of diffuse positive charge. While Thomson's results provided information about the mass-to-charge ratio of an electron, we still did not know the exact charge or mass of an electron. In the early 1900s, Robert Millikan determined the charge of an electron through what is now referred to as the oil drop experiment. He used X-rays to ionize air in a chamber containing oil drops falling due to gravity. The X-rays cause negatively charged electrons to form and attach to the falling oil droplets. With a positively charged metal plate at the top of the chamber and a negatively charged plate at the bottom, the negatively charged oil droplets were attracted upwards to the top plate while gravity pulled them down towards the bottom. By measuring how much the drops rose or fell depending on the voltage between the plates, Millikan was able to calculate the charge of the electron. The oil droplets all had charges that were multiples of 1.6 times 10 to the negative 19 coulombs because they had a different number of electrons attached to them. This indicates that the charge of a single electron is negative 1.6 times 10 to the minus 19 coulombs. Further, because Thomson had determined the mass-to-charge ratio of an electron, Millikan could then easily calculate that the mass of an electron is 9.10 times 10 to the minus 28 grams. For comparison, the mass of a hydrogen atom is 1.67 times 10 to the minus 24 grams, so Millikan's experiment had confirmed Thomson's theory that subatomic particles, which are smaller than a hydrogen atom, exist. The plum pudding model of an atom developed by Thomson was only a theory and had not been verified. In 1911, Ernst Rutherford performed further experiments and disproved that atoms were anything like blueberry muffins. Rutherford fired positively charged alpha particles at a thin gold film. He then measured whether the alpha particles went through the foil or were deflected. If atoms contained a cloud of positive charge, as postulated by Thomson, it would be expected that most of the alpha particles would be deflected, since the positive charge of the atom cloud would repel their positive charge. Instead, most of the alpha particles went straight through the gold foil. A few were deflected at angles, and some rebounded directly back towards the alpha particle source. Rutherford concluded that the atom could not be a cloud of positive charge with embedded electrons, but rather it was likely the opposite, a cloud of electrons with a small dense center of positive charge known as the nucleus. Since most of the volume of the atom is taken up by electrons around the nucleus, it makes sense that most positive alpha particles would pass through the foil easily, while a few would be deflected if they were heading directly towards an atom's positive nucleus. In the next video, we will show how Rutherford's work contributes to the current understandings of atomic structure. So, as you can see, finding the correct structure of the atom required patience, innovation, and rigorous experimentation. Thomson's experiments with a cathode ray tube established that an atom is divisible and contains negatively charged electrons. While he noted the correct mass-to-charge ratio of the atom, his plum pudding model was foiled by Rutherford's gold foil experiment. Millikan built on Thomson's results, and using the oil drop experiment, he established the charge and mass of an electron. Finally, based on an experiment with alpha particles and gold foil, Rutherford proposed a model of an atom with a dense positively charged nucleus and electrons surrounding the nucleus. While it may have taken hundreds of years for us to begin to understand the structure of an atom. Hopefully you had a positive experience learning about it in the last few minutes.